Hello everyone and welcome to Soros's classes once again. This video is about LPP and it deals with the sensitivity analysis. After LPP is solved, it may be desirable to study how the current solution changes when the parameter of the problems are changed. In many practical problems, this information is much more important than the single result provided by the given optimal solution. The changes in parameter of the problem may be discrete or continuous. The study of the effect of discrete changes in parameters on the optimal solution is called sensitivity analysis or post-optimal analysis, while that of the simulation changes in parameters is called parametric programming. The changes in the LPP, which are usually studied by sensitivity analysis, include number 1, changes in the requirement vector B, changes in the cost vector C, changes in the element of coefficient matrix A, structural changes due to addition or deletion of some variables, structural changes due to addition or deletion of some linear constants. After the above mentioned changes have been affected in LPP, we may have any of the following cases. Number 1 is the optimal solution remains unaltered. Optimal solution is not changed. Number 2, the basic variables remains the same but their values undergoes changes. Basic variables is same but value changes. And number 3, the basic solution gets changed entirely. Now, sensitivity analysis is also called post-optimality analysis because it is done after an optimal solution, assuming a given set of parameters has been optimal for the model. Now students, let's move on to the next topic, that is parametric linear programming. So far we have considered sensitivity analysis for one decision variable, assuming that all parameters of the problem remains constant. For example, when we examine the range of a particular right-hand value over which the current basis will be remained unchanged, it is implicitly assumed that all the other RHS values will remain constant. Now students, we consider the following problem. 4 similar products G1, G2, G3 and G4 are being manufactured by a company in any combination which have profit rates as Rs 70, Rs 65, Rs 80, Rs 75 respectively. 2 types of raw materials M1 and M2 and 2 types of man-force F1 and F2 are required for the above products. The per unit demand and the availability of the resources is. Now let's draw the table. This column is for availability. And this is requirement. The values are 4, 4, 3, 7, 6, 3, 5, 4, 5, 2, 3, 3, 6, 5, 1, 2. Now the problem states that we need to examine whether the current basis would remain unchanged under each of the two cases. Case 1 is the profit per unit of G1 increases to rupees 100 and the profit per unit of G4 decreases to rupees 65. Case 2 says that the unit profit for G1 increases to rupees 115 while for G4 increases to rupees 130. Now the solution. Now students, in both the above cases, the changes are indicated in G1 and G4, both of which have non-zero del J values. Hence the cases fall in the category A. The ranges determined in the previous problems are G1 from negative infinity to 127.50, G2 from negative infinity to 103.33. In both the changes are within the allowable ranges, thus there will be no change in the basis. In B, the change for G1 is within the allowable limit, but for G4 it exceeds the limit. Hence the problem needs to be resolved and the current basis is no longer optimal. Therefore this is G4. For the first case, we see that both the changes are within allowable ranges. Therefore, no change basis will take place. And in 2, the change for G1 is within the allowable range, but for G2 it exceeds. Therefore, we need to resolve the given problem. Now students, in the second category, that is category B, we may often show that in many cases when the changes take place in the objective function coefficients, the current basis remain optimal by what is known as 100% rule. Now let us explain the 100% rule. Let Cj is equal to coefficient of the variable xj in the objective function. And del Cj be equal to the change in the coefficient that is equal to the difference between the new and old values. Ij is equal to the maximum allowable increase in Cj for which the current basis remains unchanged. And dj is the maximum allowable decrease in Cj for which the current basis remains unchanged. Now we define a ratio Rj where Rj is equal to the actual change in Cj, that is del Cj, divided by Ij, or the maximum allowable change in it, if this formula is applicable if del Cj is greater than 0. Else, if del Cj is less than 0, then we see that Rj is equal to negative of del Cj divided by del J. If the coefficients of certain variable does not change, that is del J is equal to 0, then Rj becomes 0. Now if only one Cj in the objective function changes while the others remain constant, then the current basis would remain optimal Rj less than 1, that is if gamma j less than 100% expressed as a percentage. The percentage rule is a generalization of this concept. According to this rule, in case of multiple changes of the objective function, the coefficients, if the summation of Rj does not exceed 100% or summation of Rj is less than equal to 100%, then the current basis shall remain unaltered. Therefore, basis not changed. Else, if summation of Rj is greater than 100%, the current basis may or may not hold valid. may or may not hold valid. Thank you.